In this video, we'll be talking about the first law of thermodynamics, and by the end of it, we'll have an equation to represent what it means. So we'll start off by defining the first law, which states that energy can change forms, but it can't be created or destroyed. And so we'll take an example to better understand what this actually means. So if we have a cup of hot cocoa, the cup, and we have some cocoa in it, and it's hot. The cocoa inside of the cup has chemical energy because of the carbohydrates inside of it and other forms of nutrients it has, and it also has heat energy. And when someone like you or I drink this cup of cocoa, we can convert it into different forms of energy. So for example, something like kinetic energy by running, kinetic energy, or we could do something else like lifting weights. I know the bar looks like it's going through the head, but it's not. So this is potential energy, and these are just a couple forms of energy that the original chemical and heat energy can change into. Now let's take a look at a piston to come up with an equation that encapsulates the first law. So we'll start out with a piston chamber, and this is the piston inside of it, a little rod right here, and this rod continues, and we'll have a second instance of the same piston. So this is just a little bit later. We have that same rod that continues, and what we're interested in is our system, which we'll define as the area inside of the piston and the piston chamber. So this whole area in both instances. We'll call this instance 1 and we'll call this instance 2. And there's two main ways that we can change the energy of a system. So the first is by adding heat. So if we had something like a fire underneath this piston chamber, we would be adding heat, and that is represented with a Q, which then pushes on the piston and moves it up. We could also do work either just pulling on the piston rod, or the system, the gas inside of the piston chamber has a greater pressure than the surrounding pressure over here. So that causes the piston to raise up as well. So we can represent the change in the energy of our system as the energy in the second instance minus the energy in the first instance. That doesn't tell us much, so we'll describe it in a little more detail using the different forms of energy that we learned in the 6th video. So in that video, on the macroscopic scale, if we think about just our system, it's not moving. So it's just on some stationary table. Let's say, so this is a table in both instances. So because this instance is not moving, we don't have any kinetic energy. So this is 0. We might also have a change in gravitational potential energy, but because this piston is still on that same table at the same height, the table isn't moving, the piston chambers aren't moving, so this is also about 0. And lastly, we have all the microscopic or internal energies. So we have that change in internal energy, which is not necessarily zero, because the sensible energy might have increased, or the average kinetic energy with molecules on the microscopic scale might have increased, and so this is non-negligible. And this is all equal to the interactions that the piston has with its surroundings. So it had a heat interaction, and it also had a work interaction. And we'll look into more detail on these two specific interactions right now. So if we have that equation, our change in internal energy is equal to our heat plus our work interactions. Now we will define heat. So given that a positive Q, or a positive heat interaction, means that it's heat added into the system, just like we have drawn in the diagram. If this is heat added into the system, we can think about the molecules on a microscopic scale. So if there's heat added, then the molecules are moving faster, so the sensible energy, or the kinetic energy of the molecules, are increasing. So we expect that the internal energy is positive. So if Q is positive, so if it's increasing, then we expect that delta U is positive and increasing. So that checks. Now let's look at the work. So given that a positive work means that there is work done by the system just like it's drawn in the diagram. So we're imagining that our system is at a higher pressure than its surroundings, so it's pushing this piston up, so it's doing work. Then once it does work on its surroundings, we expect the internal energy of a system to decrease, because some of that internal energy was used to push the piston up against the pressure of the surroundings. So expect that the internal energy of our system to decrease. Let's check our equation. So if work increases, right now the internal energy also increases, but we need it to decrease. In order to do that, we can rewrite the equation as the change in internal energy is equal to the heat interaction, which we determined was positive above, and then we can subtract the work interaction to get the relationship that we want. And this we know from this equation up here, that this is all equal to the change in energy of our system. And this is an equation that describes our first law. Thank you for joining me on this video. I'll see you in the next one.